Hello, everyone. We are discussing another machine learning algorithm. It's called support vector machine. There's three parts to the series on support vector machine. The first one is maximal margin classifier. We will talk about support vector machine as a classification technique. Specifically, it's a supervised method. It's non-probabilistic, it's a linear method, and it is a binary classifier. So we'll spend some time defining what each of these means. This algorithm was invented by an applied mathematician from Russia. His name is Dr. Vapnik. He is still on the faculty of Columbia University, so you can go ahead and take a look at his profile if you're interested to learn more. This approach comes from the discipline of computer science, so it's very different from the statistic-based approaches we have been looking at so far in this course. It is a supervised method, meaning that we need to provide the algorithm with correct Y labels. It is not based on statistics. You will see it's based on a lot of algebra, a lot of geometry, and measuring distances and using optimization mathematics to figure out the best lines. It is linear for the most part, at least for the base models, and then later on we'll look at the nonlinear versions. Is a binary classifier, so basically the goal is to sort your Y values into two piles: yes, no, 0, 1, positive, negative, and so on and so forth. We will see that support vector machine has a lot of different versions. There's been a lot of enhancement. The most basic version is called the maximal margin classifier, which is what we focus on in this lecture. The next lecture, we'll talk about support vector classifier. And then the third lecture, we'll focus on the real support vector machine. So this is what we're focusing on in this lecture. It is for linearly separable classes only. So what do we mean by linearly separable classes? So different data sets present different classification problems. Here is sort of the easiest classification problem, which means that we have two classes of data and they can be perfectly separated by a single line. If you look at this example over here, we have two dimensions of data. So X1 is credit score, X2 is mortgage, and we have data values that vary along these two dimensions. The labels for the Y variable are actually indicated by the color and the shape of the data points. So the yellow dots is one class and the green crosses is another class. So that's your yes, no, 0, 1 classes. So the Y labels are not actually labeled on the Y axis. I just want to point that out. The Y axis now shows an X variable. However, we can see that the Y labels can be clearly separated into two classes, and you could do that with a simple line. However, there are actually many different lines you can draw. And in fact, there are infinitely many lines that you can draw. So the question is, which one is the best line? So this becomes a very straightforward optimization problem. We want to look at all possible values and want to pick the best one. The best line is defined as a line that is the farthest from both classes of data. So we want a line that's as far as you can get from the green crosses. At the same time, it's also as far as it can be from the yellow dots. So basically, you want to find a middle ground that is of equal distance to both classes. This is how the data frame might look like. So I just want to sort of connect the visual chart to the data set. So this is in R, when you look at your data frame, this is what your data frame will look like. You will have two X columns. They can be numeric, they can be categorical. In this particular case, we have numeric X values. The Y is always categorical because we're doing a classifier. You can see the Y column can have two possible values, the green class and the yellow class. The line can be represented as a linear equation. Beta 0 plus beta 1, x1 plus beta 2, x2 equals 0. So if we represent the line as such equation, then we can basically represent the green classes, the green dots, or I'm sorry, the green crosses as the equation less than 0, and the yellow dots on the other side of the line, and they are in the space that's greater than 0. So this is how we would mathematically represent this problem. The line is actually a very specific case of the general idea of a hyperplane. We can talk about hyperplanes in general in any kind of dimension, because you may not just have two x's, right? So you can have up to p x features. So if you have px features, you are actually working in a p-dimensional space, and we can represent the line. It's no longer a line, right? So the line is just a hyperplane in a two-dimensional space. You can actually have many different hyperplanes in a p-dimensional space. Usually you cannot really draw a hyperplane that's more than 3 dimensions. So on a 3-dimensional space, you would draw it as it's almost like a piece of paper, right? So it's a flat sort of surface. However, you can also extend that to 4 dimensions, 5 dimensions, and so on. And that the idea is that flat surface, the line or a hyperplane, will be able to divide the data set into two perfectly separated classes. Again, the idea is to pick a hyperplane that is the farthest from both classes of data, whether the hyperplane is a line, a flat surface, or some multi-dimensional shape. So we can extend the linear equation to p dimensions using this formula. Again, the hyperplane is the spot where everything add up to 0, and then the green class is in the space where the equation is less than 0, and the yellow dots are in the space where the equation is greater than 0. So here, let's look at a very, very simple example that involves only one x variable. So you can see the dots are lined up along the x dimension. It's credit score, and we have two classes of the y target variable. So we have those customers who default. So that is indicated by the green crosses, and the yellow dots represent the other class, which is the customers who did not default. So they're the yellow dots on the right-hand side. So in order to find a model that will separate these two classes, we can simply draw a line. Oh, this is the data set, right? So this is what this visual will look like when you construct a data frame. So you will have an X column with these values. Some of them are lower, so you can see the Y labels, the green crosses, they tend to have lower X scores. And then the yellow class, the yellow dots, tend to have higher credit scores. Okay, so this is how they will show up in the data frame. And the idea is that you want to find a line that would separate the two classes. As you can see, you can draw a line anywhere between the two classes, and the line will separate them very well. Now, this may not be the best model, but it is a model that you can come up with, and it's indicated by this blue line here. So using the blue line, we can actually make a prediction on a new data point. So this is our test data, which is a white star. And the question is, we want to know if it's, we want to make a prediction about whether this customer is going to default or it's not going to default. Okay. So you can see in the data chart, this star has a pretty low credit score. It has a score of 280. So it's definitely sort of on the lower end of the X, and it falls in the region where the green crosses cluster. So using the blue line, because the blue line is our model, the model helps us separate the classes into two clusters. And what we do is we basically use the blue line to make a decision. Well, since the test data point, the star is on the left-hand side of the blue line, we will predict it to be in the default class, which is probably reasonable. So the prediction is the green cross. Now let's look at the data set again with a new test point. So here we have a new test data value, and it's a credit score of 760. So this white star, it's on the higher end, and it's on the right-hand side of the blue line. So we'll make a prediction that it's not going to default. And because it's close to all the yellow dots, that prediction is reasonable. It's probably a good prediction. Now let's look at another example. Here we have a new customer, a test data value that is 410. Okay, so it is sort of on the lower end, and it's actually pretty close to all the green crosses. However, it is on the right-hand side of the blue line. So the blue line, which is our prediction model, will actually predict this customer to be a yellow dot because it's on the right-hand side. However, because it's closer to the green crosses, it's probably not going to be a good customer. This is probably going to be a customer that's going to default. So this is going to be most likely a misclassification, okay, a prediction error. The problem is the reason why we would make that prediction error is because our blue line was not really separating the classes in a very fair, right, way. It was very close to the green crosses. So an easy solution is to look at the distance, the space between the two classes. We can find the boundary points. Sort of the data points are on the border of each class. And then we can measure the distance, and we can say, well, let's take a look at the distance and find the middle ground. And that's where we're going to draw this line. Okay, so a better and more sort of systematic and a more sensible approach to draw your blue line is to find a line that maximizes the distance from either class. So in that particular case, if we do that, then when we are presented with this test data value of 410, then we'll be able to make a correct prediction that this new customer is going to default. This is now, it falls on the left-hand side of the blue line, and the blue line will be able to make that prediction correctly. So what we have seen is what we call the maximal margin classifier. It's basically an approach to draw a line that maximizes the margin on either side. Okay, so the margin is basically the distance to one of the classes. So in this particular graph, we see that there are two margins, one on each side of the line, and we want to be able to maximize both margins at the same time. The maximal margin classifier is also sometimes called the large margin classifier. So you will hear both terminologies in the literature. And as we have seen, the idea is to maximize the margins on both sides. How do you measure the margins? The margins are determined by the boundary data points. The boundary data points are called support vectors. So these points that are on the boundary that determines where your margins are. Each one of them is a support vector, and that's how actually the name of the support vector machine algorithm comes from. The support vectors are very important because they basically determine where we draw lines. You can also determine how many support vectors you want to include, and you can be flexible, you can be rigid. So the support vectors will actually alter the shape of your classifier. It'll alter where it is. So determine how accurate the predictions are. So all sorts of stuff. So the support vectors are very important. You want to keep that in mind. Those are basically a bunch of data points on the borders. Now let's go back and look at a two-dimensional maximal margin classifier. So now we have the y values distributed across two x dimensions. Again, we're looking at a linearly separable problem, and we want to find a line that is far away from both groups of data. So what you want to do is you want to find some support vectors. So we could see there are crosses, there's a cross and a dot that are on the border, and we can use those points to draw the margin lines. And then what we do is we find the line that's in between this maximal margin that's right in the middle. That becomes our maximal margin classifier. So what we have talked about, it basically goes over this idea that's discussed in your textbook, that we have two sets of classes, the blue dots and the pink dots from your textbook. And there are many, many different ways to draw lines to separate the two. What we want to do is we want to find the best line, right? So many potential classifiers are possible. The maximal margin classifier is the one that's optimized. How do we optimize the line? Well, we find the support vectors, we draw the margins, and we find the line that is far away from both, from support vectors from both sides. Okay, so you can see in this particular example, we have 3 support vectors that are on the line. The hyperplanes, or in this particular case, the lines are just 2-dimensional hyperplanes, can be represented as these 3 linear equations. And using these equations, we can represent the problem as a convex optimization problem with the objective function to maximize the margin M, the value that is the size of the margins. So the math is probably more complicated than we need to discuss in this course. The solution of this optimization problem is already written up as the SVM function in the library E1071. It is a really bizarre name for a library. And R is the dorm room number of the person who invented the algorithm, well, who wrote up the SVM algorithm for R. So what you want to do is you just want to call the library and run the SVM function, and that function basically implements the convex optimization solution. Maximal margin classifier is very easy to understand, makes a lot of sense, but because it's very simplistic, it's also very limited in a lot of ways. Most importantly, it's unable to handle outliers. So basically, we're trying to draw a line. So what if you have data that's not perfectly clean and separable. In this particular case, the data set is separable. It's linearly separable. We can find a line that divides the two. However, you can see that the green class is an outlier. There's this one dot that is very far away from the rest of the class. So if you just draw a line to accommodate this outlier, you'll come up with the blue line, which is the model that perfectly separates the training data set, but it's very bad at predicting what happens with the test set. Okay, so it will misclassify the test data set, which, this one, this white star should probably be classified as a yellow dot. However, because the line has to accommodate the outlier, the line actually would classify the test data value, the white star, as the green class, which is a misclassification. So that's a problem with maximal margin classifier. In the next lecture, we'll see how we can improve upon this using some enhancements. So to recap, we have had an introduction to support vector machine as a supervised training method. It's non-probabilistic, so hopefully you've noticed that we did not talk about probability at all. We were just measuring distances and solving linear equations. It is a binary classifier. It is linearly based. And we have talked about one of the 3 different methods to implement support vector machine. This is the most basic version, maximal margin classifier. Uses a hyperplan to separate classes. The hyperplane is determined by the support vectors, and it's determined using optimization to find the optimal margins to either side. It is easy to understand, but it is also very sensitive to outliers, so it doesn't work very well. It has a lot of variance problems, right? So the bias variance trade-off, when you perfectly separate the data, you're basically overfitting, and your model has very low bias, but it has very high variance, meaning that it is unable to make accurate predictions on the test data set. So that's all. I hope you enjoyed the lecture, and let me know if you have any questions.